Am I audible? Okay. So this is more of a physics talk compared, like similar to the previous one, than the talks on the GPUs. And I'll be talking about the like impact of nuclear geometry on symmetry plane code. So this is again, so starting with a basic introduction. So on QCP and heavy ion collisions, and this is already discussed in the previous talk. So I quickly and go towards flow and symmetry plane correlations, which is core part of the like study. Then I'll discuss shortly about the oxygen and collision, their geometry and the model calculation, simulation, and the computations that have, then the results, and finally summary. So as you already know, the matter is composed of molecules and atoms. Each atom has electrons and nucleus. The nucleus has protons and neutrons, and protons we have quarks and gluons. So normal circumstances, the quarks and gluons cannot exist freely because of the property of uh, QCD known as color confinement. But if you heat it up to a threshold, uh, uh, like obtain a local like localized volume. So the pattern that existed in the inverse in the microsecond inverse. So create this? How to create this in the laboratory? So thank you. We can like collide heavy ions such as lead, gold, and so. And the collision then takes place, and we have initial state where like partons are there. The thermalized to form QCP, and then they evolve through different phases, and finally the particles are detected in the detectors. Before I go to the further uh, my further slides, I'll just introduce some terminologies quickly. So here, okay. So sorry, yeah. Oh, okay. Okay, so we have like two incoming ions colliding, and we have this yellow thing, which is the system formed, and a particle is emitted with momentum p. This momentum can be resolved into different axes, px, py, pz, and using that we can calculate different observables such as transverse momentum, azimuthal angle, polar angle, rapidity, and rapidity. Then, depending upon their impact parameter, the a collision can be isolated into different centralities, such as if they collide with almost zero impact parameter, we have central collisions where the final state charge particle multiplicity is high. And if they collide with finite multiplicity or collide with large impact parameters, the collision is termed as peripheral collision, so where we have low multiplicity. So, uh, as mentioned in the previous talk as well, so this coagulant plasma is short-lived and we cannot directly observe it because of the property called color confinement. So we have indirect signatures such as collectivity. The anesthetic flow is well known to probe the collectivity of the system, and in like because of the fluctuating distributions of nucleons, the overlap region can have a different initial anisotropies. And if a elliptic, like I'm giving an example of the elliptic nature here. So if the initial spatial anisotropy is elliptic in nature, then we have elliptic flow in the final state, which where the momentum distribution is kind of looks like ellipse. So this final state momentum anisotropy can be quantified using the coefficients of Fourier expansion of the azimuthal distortion of particles shown in the left one, and then we can extract this Vian coefficients, which will tell us about the final state coefficients. So the collision of a left region can be decomposed into elliptic, triangular, quadrangular, and so on. So it goes to infinity as actually. So, but the contribution reduces to each contributor we have. So the triangular thing I'm showing here. So this is the elliptic emission, triangular emission, and quadrangular emission. So each, if you draw a symmetry line here, and the closest to the x-axis, then we have an angle. We call it the second order symmetry plane angle. So it is called as psi2. Similarly, for triangular shape, we have psi3 and psi4 and so on. So if you look here, so for the n equal to psi2 and psi3 seem independent, but psi4 can be again decomposed into two combination of psi2 and so similarly, if you go to n equal to 5, we can have contribution from psi3 and psi2 and so on. So this gives us a scope to understand the final state symmetry planes and in terms of their correlation. So I already told how the SPCs are important, but why not just study the single symmetry planes? Because we cannot do that because for a large event sample, they have the average value 0 because they align randomly for different events. And so we study the symmetry plane correlations, which is usually studied by this observable here. And as I already mentioned, they are they separate linear responses from non-linear hydrodynamic mixing, such as V4 into 2 V2 square and so on. Similar to flow coefficients discussed in the previous presentation, symmetry plane correlations are also sensitive to the initial geometry and the properties of quark-gluon plasma. So I'll not go into the details of the slide. So we can calculate the symmetry plane correlations using the different particle correlators. It depends depending upon the order. And we for this work, I'm focusing on these two symmetry plane angles. So this is between psi2 and psi4, psi3 and psi6. And the region I'll be mentioning soon. And these are basically 3 particle correlators. For the oxygen, we see that they are kind of 4 alpha particles clustered together in the tetrahedral nature shape. For if we put another alpha particles, they kind of look like a pinball, and neon is structured like that. So the oxygen nuclei has an intrinsic octupole deformation, and the octupole deformation are well quantified by using this symmetry plane angle. Similarly, for the neon, we have large quadrupole deformation in the nuclei, and this can be well quantified using this observable when 2 neons collide. For this study, I am using a multiphase transport model, which has 4 parts listed here. And since the collisions at the LSC produce lots of patterns in the patterning phase, and then thousands of particles in the final state, they require lots of calculations to for their evolution. So yeah, and the focus of the study is to the focus is on the nuclear geometry. So the central collisions are even better for us, and which requires even more computing power. For the symmetry plane correlations, again, if an event has m multiplicity or m charged particles, it requires around this much of computing cost. So where n event we have, and n combination of harmonics, and k particle correlators, and m is the multiplicity. So it increases with the number of correlators we have, number of events we want to simulate, the number of charged particles we need. And the table shows the computation cost that increases with if we have multiplicity of 3000 for event. So we have used the CPU cores in the Wigner machine, and the workflow is following. Okay, so first of all, the transport model I'm using is an old Photon 77 code, and it does not have a intrinsic parallelization. So we wrote a basically bash script which creates several copies of this file and runs them into several cores simultaneously. So each of these simulation creates separate root files, and then I run the symmetry plane correlations parallelly on each of these root files, and I obtain the final output. Then which are merged together for my results. So as a results, as I discussed, the neon seem to have larger the correlation between site 2 and site 4, which is expected because of its intrinsic quadrupole deformation. On the other hand, the oxygen seem to have higher correlation between site 3 and site 6 because of its octopole deformation. These are again visible clearly in the lower panel, in the ratio panel. I tried to study these results for tip and body selections, and we see that the correlator site 2 and site 4, which depends upon the overlap geometry, are sensitive to tip and body collisions, and on the other hand, site 3 and site 6, which are driven due to fluctuation, depend weakly upon that. To summarize my results, we have studies like two correlators, symmetry plane correlators in oxygen union, and they seem to agree with their assumption about the quadrupole and octupole deformations. And as outlook, the study is performed on a transport model, but it will be interesting to extend it to hydrodynamic evolutions and another higher order symmetry plane correlation that can tell more about the intrinsic nuclear configuration, the overlap region, and their evolution in the final state. So this is all, and thank you. And yeah.
So thank you for the talk. We have plenty of time for question for Suraj.
Hi, Suraj. Talk. Do you think this can be turned to an Alice analysis at a certain point?
Alice analysis. I think it is ongoing. And recently I have been added to the analysis because of this publication. The paper committee saw this and they asked me if I can contribute for the simulation results, and I agreed. So yeah, this is still ongoing, and they are extending this to higher coefficients. So so the results I showed today are basically 3 particle correlators, and they are even going for 6 and 7 particle correlators. So the analysis are even like in greater magnitude compared to the results I'm showing today. And okay, so my results seem to agree with the results they obtained.